Hi everybody, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And as it turns out, I'm almost done with chapter 6, which is on group theory. I'm just going to have a couple more videos after this one, I think. But today I'm going to talk about a very important class of infinite groups known as wallpaper groups. And these are just the pattern, the groups corresponding to every type of wallpaper pattern. I might as well show you a picture here. So anyway, it turns out there's 17 different types of wallpaper patterns. I'm going to talk about each one. And here's just pictures of them, and they all have IUC symbols associated with them. You don't have to memorize these symbols. Maybe you'll kind of see the logic associated with them as I go over them. Before I get into them, I just want to say one kind of interesting fact about these groups. They weren't first classified completely until I think the late 19th century. I mean, group theory wasn't even invented until the early 19th century. So this wasn't too long after group theory was discovered. And so, the concept of groups was known, and then it was also known that groups, there was important connections between group theory and symmetry, and then I think sometime in the late 19th century, I don't know who it was, but I think it was actually a crystallographer who classified these 17 wallpaper groups, as well as the 7 freeze groups I went over yesterday. And in addition, there's 230 crystallographic groups. These are three-dimensional analogs of these wallpaper groups. So I think the number grows pretty fast with dimension. I don't know if anybody's classified in dimensions bigger than 3. I'm pretty sure that some people have, but pretty amazing, I think, that all 230 crystallographic groups have been identified and classified. I'll talk about that, I think, in the next video, but I'm not going to go over all 230. But anyway, I am going to go over all 17 of these wallpaper patterns. So anyway, let's begin. So I'm going to go from the simplest to the most complicated, or if you like, the ones with the least symmetry to the ones with the most symmetry. And I think the simplest of all the wallpaper groups is P1. And this group there's only 2 generators for this group, namely 2 translations. I think every wallpaper group has at least 2 translational symmetries. Meaning, I think if you look at these flowers here, you notice that, every flower gets repeated. I mean, for instance, it gets repeated to the right. If you go about, I guess in this picture I'm showing you about a little over half the distance of, the horizontal distance displayed in this picture, you get another flower that looks exactly the same. But you don't have to just go in that direction. You could go, kind of up and to the right, and then you'll get this another repeating. So there's 2 periods. Every lattice has 2 periods, but these are the only symmetries. There's no mirror symmetries. There's no, rotation symmetries, and there's no glide reflection symmetry. Just 2 translations. So that's the kind of the bare minimum that a wallpaper group can have. And then I guess the next simplest would be P2. This is sort of like P1, except it has an additional symmetry, namely twofold symmetry. So, for instance, you can rotate 180 degrees about certain points in this picture, like the center of the daisies or the center of the kind of, I don't know what you call that. It looks like a rope that's kind of going between these points on the alternative rows. But you get the idea. There's also a twofold symmetry associated with this pattern. And then the next one would be PM. This one, in addition to translation, this has one mirror symmetry. It has a mirror symmetry. So this is the first one that has a reflection symmetry. You notice these starfish here. You could reflect. Each of these starfish has a bilateral axis, vertical axis. So you could reflect the pattern about a vertical line passing through the centers of any of these starfish, you'll still look the same. So that's PM. Um, and then I guess M stands for mirror. 2 stands for twofold. Like I said, 1, I guess, because it doesn't have any rotational symmetry. One fold, if you like, you have to rotate it 360 degrees to get it to look the same. This one, P2, means it's a twofold rotational symmetry, 180-degree rotation, like I mentioned. M for mirror. I think you get the idea of how this nomenclature. The fourth one is PG. This one has what's called a glide symmetry, 2 glide symmetries actually. And I think I talked about glide symmetries yesterday in connection with freeze groups. Glide symmetry, it's kind of a complicated symmetry. A glide reflection is a combination of a ordinary reflection and a translation. So in order for this, it obviously has, it turns out that the 2 glide reflections generate this group. You get the translations for free. But maybe I should just talk about one of these glide reflections. So I guess what you could do is you could take, say, a point on, how do I do this? Yeah, you take a point on. You notice that there's kind of wavy rows, triangular wave rows. There are, I guess, kind of beige ones and black ones. Let's just take a point, say a point on the black one, and then we can do a glide reflection about that point and end up with the row above. I think that's how this works. I'm not 100% sure. But there's actually 2 glide reflections. I guess you have to use another glide reflection to get back to the row we started in. Anyway, so that's PG. And then the fifth one is CM. I think these ones get prettier and prettier the more symmetry they have. Maybe that's just me. I don't know. Maybe you guys can tell me what you think. But this one is known as CM. And this is and you know what? Another feature of these wallpaper groups is a lot of them have a specific type of lattice associated with them. I think the first 4 I just showed you have kind of an arbitrary lattice, not really a symmetric lattice, but this one has what's called a rhombic lattice, meaning that the 2 generators of the lattice have to have the same length. So if you like the kind of the I think they call this the fundamental region of this lattice as a rhombus, and I think you guys know that a rhombus is a quadrilateral with sides of equal length. They don't have to have equal angles like a square, but they do have to have equal length. And that's the case for the lattice of this particular wallpaper pattern. And this one, CM, has again 2 translational symmetries, like all of them do, and it also has 1 mirror symmetry. And I think you can see the mirror symmetry. I mean, if you just reflect a figure about a vertical line, say the vertical line passing through the center of this whole diagram, you'll see it'll look the same if you reflect about that axis. So anyway, that's CM. I guess kind of similar to PM. Couple back. The only difference is PM has kind of an arbitrary shaped lattice, and CM has a rhombic lattice. And then number 6, PMM. This one has a rectangular lattice now. So we haven't talked about any with rectangular lattices yet. That's just a lattice where the 2 generators of the lattice are orthogonal or perpendicular to each other, but they don't have to have the same. As a matter of fact, they don't have the same length. But then this particular wallpaper pattern, in addition to having a rectangular lattice, it has 2 mutually perpendicular reflection axes. Let's see if we can see that. Not so easy to see, maybe because of the way they colored this thing. Yeah, actually, yeah, they're diagonal. In this case, the reflection axes are diagonal. So I think you can see there's a mirror axis that goes along the red squares up and to the left, but then there's another one that goes up and to the right. So those are mutually perpendicular. Yeah, I don't know why they showed this pattern at a 45-degree angle. Maybe it just looks a lot more artistic that way. Anyway, that's PMM, and then the next one is PMG. This is the seventh one, a seventh out of 17. And this one is, again, it has a rectangular lattice, but this one has a glide reflection generator in addition to a single. Um, is that right? Yeah, no, two. Yeah, single twofold. So it has two generators: a glide reflection, and I think you can see glide reflection will take you from, say, one red wave to the next red wave. But in addition to that, it has a twofold symmetry. So, for instance, if you rotated the figure about, I guess I have to find a point here where it has twofold symmetry. Not so easy to see. I can kind of see it. It's a little hard to describe, but if you look at a point, say on one of these beige waves that's sort of halfway between the two red waves was sort of going down, then if you do that, if you rotate them about that point 180 degrees, it will look the same. I can kind of see that, but it's a little hard for me to describe. I don't have a pointer, but anyway, that's some um, PMG. And then the next one, the eighth one I'm talking about here, is PGG. This again has a rectangular lattice. And this one has a lot of generators. It has two glide reflections and two mutually perpendicular twofold um, rotations. And I don't know if there's an easy way to see that. Um, yeah, I'm not going to even bother trying to describe where they are in this picture. You can kind of look at the picture and admire it. Yeah, that's true. You'll just have to take my word for that. Anyway, the ninth one, CMM. This one I like. This one has a rhombic lattice. Remember, I think CM, that was four back. I'm just going to go back to that one. Yeah, CM, this one was also very pretty. Has a rhombic lattice, but CMM has an additional twofold rotation. Rotation. So you'll notice that it has like, I mean, the other one, all the figures they look like vases. They were all upright. This one is symmetric about a horizontal axis. The other one wasn't. The other one was symmetric about just a vertical axis. And remember, I talked about that. You could reflect the whole thing about the axis, the vertical axis passing through the center of the picture. A lot of other vertical axes too, but no horizontal axis for that one. But this one, I think you can see that you can reflect this one by horizontal axes as well as vertical axes, and it still looks the same. And I like this one. I don't know. I just like the ones with more symmetry for some reason. I don't know. I was pretty fascinated by symmetry. I guess to each his own. Maybe a lot of people, when they're putting up wallpaper, maybe they don't want a wallpaper that looks too symmetric. I don't know. I don't know. Number 10. This one's called P4. This is the first lattice I'm talking about that has a square lattice. So not just a rectangular lattice, but a square lattice. The lattice has two generators of the same length that are mutually perpendicular. And not only that, but this wallpaper pattern has a fourfold. It has two fourfold generators and one twofold. So I think you'll notice that, for instance, if you rotated 90 degrees about the center of any of these daisies, it would look the same. But not only that, if you rotated about one of the red squares 90 degrees, it would look the same. So those are two fourfold generators, but then you also have twofold generators. For instance, if you looked at a point on one of the edges between the daisies and the squares, if you look at kind of the vertex where two squares and two daisies meet, if you rotated 100, you'd have to rotate 180 degrees about that point for it to look the same. So that's a twofold rotation axis. So anyway, that's P4. 4 stands for fourfold symmetry. I guess it's the simplest lattice pattern with fourfold symmetry. But then you've got a couple more. You've got a couple with more symmetry to them. P4M, in addition, has two. This one has two twofold rotation axes. And I think that also gives rise to a mirror symmetry. I'm not sure. But yeah. Anyway, you'll just have to take my word for this. You can see this one has more symmetry than this one. For instance, there's no mirror symmetry in this one. I believe there is mirror symmetry in P4M. M stands for mirror reflection, so it has to have a mirror symmetry. Uh, and then the 12th one is P4G. This one looks kind of complicated. I kind of like this pattern. Kind of looks like a piano curve, a space filling curve, I think it is. Um, anyway, this particular pattern, again, it has a square lattice, and this one has two fourfold rotation axes that are all mirror images of each other. I don't know if I want to describe them all, but I think you can see it has a lot of vertical and horizontal symmetry. Pretty cool looking pattern, I think, but a pretty complicated symmetry corresponding to this group P4G. That takes care of all the square lattices, and now we have hexagonal lattices. I think these are my favorite. And the simplest wallpaper pattern with a hexagonal symmetry, a hexagonal lattice, is called P3, and the 3 means it has a threefold symmetry. And I think this picture, I recognize this picture. I think this is one of the patterns at the Alhambra. Yeah, one thing I forgot to mention, I should have mentioned this earlier when I was talking about wallpaper groups. There's a very famous temple in Spain called the Alhambra. It's a Moorish temple. It was built in the 14th century. Um, and a beautiful temple. And what's interesting about it, this is actually one of, they have all these stained glass windows with all these wallpaper patterns. It turns out they didn't know they were wallpaper patterns, but they knew they were neat looking patterns with a lot of symmetry, a lot of interesting geometry. And I guess the Moors were interested in geometry. Uh, you know. The Arabs invented a lot of cool math, before the Europeans. So I think the Arabs knew about symmetry a long time before the Europeans did. They didn't. I don't think they ever invented group theory. But what's interesting about the Alhambra is that all they do display windows with all 17 wallpaper patterns. They just exhausted all the possibilities. They didn't classify them all, as far as I know. But they kept trying to find whatever patterns they could that had whatever kind of symmetries they could find, and it turned out they used them all up. So they did this 500 years before they were classified. I think that's pretty interesting. And this is one of them. And this is P3. What that means is it has actually, it has three threefold generators. So there's three different kinds of points in this figure where if you rotate it 120 degrees, it would look the same. Except for the colors in this case, they colored the portions differently. So strictly speaking, this isn't the wallpaper pattern I'm talking about if you include color, but forget the color, and it is a pattern with the wallpaper pattern P3. And I think you can see if you rotate 120 degrees about the center of any star, it'll look the same. Also, if you rotate it about, you kind of see these three blades. They have these kind of white circles. If you rotate 120 degrees about any of those points, it would look the same. And I think there's a third. Oh, yeah. Well, you see where the three blades meet. So you have a point where the three kind of green blades meet. And if you rotate about that point by 120 degrees, it would also look the same. So that's P3. Kind of neat. The next one, 14th one on my list, is P3M1. This is another one with a hexagonal lattice. And this one, in addition to having threefold rotation axes like P3 did, it also has three glide reflections. And I think you can see that a glide reflection will take you from one of these hexagons to another hexagon. And it turns out the glide reflections are 120 degrees apart from each other. Anyway, so that's P3M1. And then P31M. This is one I really like. This one, again, has a hexagonal lattice. Yeah, and this one, again, has three threefold generators. But the threefold generators are all mirror images of each other, unlike P3. So these kind of have special orientations for the threefold generators. So it has a little bit more symmetry than P3. And I think you can kind of see that. I mean, these daisies or whatever they are with the three petals, they're upright, and the one I had before they weren't. And they have mirror symmetries in the middle of each of them. I don't think P3 itself had any mirror symmetries, but P3M1 does. So a little bit more symmetry than P3. This is P3 1M. So that's the 15th. Now just two more. The next one is P6. And this is sort of like P3, except now you have a six-fold rotation axis. So this actually has six-fold symmetry. None of the ones I talked about before had six-fold symmetry, just threefold. But I think you can see, these daisies in this picture, they have six petals, and if you rotate just 60 degrees, the picture would look the same. And you don't have to just, it also has threefold axes too. If you look at these triangles, those are threefold axes, but the center of all the daisies are sixfold axes. So I think that's kind of a neat one. One last one. The last one, the one with the most symmetry, is P6M. Once again, this one has sixfold rotational symmetry, but in addition to that, it also has mirror symmetry. P6, remember M stands for mirror. P6 doesn't have any mirror symmetry, but it's P6M does. So I think P6M has the maximal possible symmetry of any wallpaper pattern. I mean, there's only a couple of them that have sixfold rotational symmetry, but this one does. It also has mirror symmetry, and it just looks really cool. So anyway, that completes my video for today on wallpaper groups. I just described all 17 of them. So anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.